It looks like you have the good fortune to be able to be working in your office.
Yes. So I actually have been allowed to come back to office throughout the pandemic because it's individual offices.
Right. Well, yeah, that's certainly the case for me as well. I can go to my office, but I can't meet with anybody. So it's a fairly pointless endeavor.
The campus is going to open up in fall anyways. So it's
yeah.
We're looking at crowds to coming back. So let's see. So we are a couple minutes away from starting the session. I'm just going to give it maybe a minute or more for all the audience to return.
It's very disappointing. I was looking forward to coming down to the campus for this meeting.
Right. But you if you are willing, you can come anytime to campus to give a talk, not at the conference, but at other platforms here.
I certainly am always happy to do that.
That'll be great.
Yeah.
Looking forward to it.
I come down there fairly often because my daughter and son-in-law live in Westlake Village.
Oh,
yeah,
that's a nice area. It's not too far. Okay. We're probably looking at hybrid seminar for this fall, but hopefully we'll all open everything up to all in-person seminars.
Yeah.
Winter, hopefully.
Hopefully that's coming, yes.
But the virus is going down the Greek alphabet, so we don't know what's going to happen.
We'll see what happens when we get to the Omega variant.
Exciting. Okay, all right. So shall we start? So welcome back, everybody, and welcome to the plenary and keynote session today. This is the keynote session number 2. My name is Yu Huan. I'm a faculty member here at the University of California, Los Angeles. So if everything were normal, we'll be meeting here today in person. But I hope this online version will serve the audience and our speakers just as well. So just a few housekeeping notes. So we'll have the question and answer sections open at the end of each presentation. And when you are unmuted, feel free to speak up, or throughout the talk, you can also post your questions in the chat box. And for those who are looking at the streaming video on YouTube, you can submit your questions and the assistant will pass those questions to me. And I will address and address them to Jim or to our speakers accordingly. We're sorry if we're not able to respond to all of the questions due to the limited time. So today in this session, we're truly honored to have some of the most distinguished scientists around the world to share their long-term contributions and recent breakthroughs in science. In this keynote session, we present 2 prominent speakers, Dr. James Diario and Dr. Yuri. And unfortunately, our third speaker, Dr. Naomi Harless, was not able to join us due to a time conflict. Okay. And so our first speaker is Dr. Jim Diario. Jim is currently a chief scientist for material synthesis and simulation across scales at Pacific Northwest National Lab. And he's also an affiliated professor of material science and engineering and of chemistry at the University of Washington. He is a fellow of the American Physics Society and the Material Research Society, as well as the member of the Washington State Academy of Sciences. Jim's research has spanned a wide range of materials-related disciplines. Most recently, his research has focused on in situ AFN and TM investigations of interactions, assembly, and crystallization in biomolecules and biomineral systems. Jim has been internationally recognized for his pioneering contribution to the understanding of material nucleation and growth, as well as for his service to the material science community. Jim has served as the president and board member for the MRS, And also he has been on the committees for the National Academy of Sciences, the Department of Energy, as well as the Congress. And for his seminal pioneering work in the material science, Jim has received multiple national and international awards. To name just a few, there are the Laudes Prize of the International Organization for Crystal Growth, the American Association of Crystal Growth Award, and MRS David Turnbull Lectureship. And most recently, Jim is named the DOE Distinguished Scientist Fellow. So with that, and without further delay, I'll pass the stage over to Jim. Jim.
Thank you very much, Yu, and thank you to you and the other organizers for inviting me to speak here today. Let me share my screen. And can you please confirm that you see it and you see it in presentation mode?
Yes, it's
Great,
showing up.
Thanks.
Mm-hmm.
Okay, so I want to talk about how functional materials are formed. One is the science of design and the other is the science of synthesis. So suppose, for example, that my goal is to achieve the kind of efficiency in catalysis that one sees in biocatalysts. There are certain features of catalysts in biology that I would like to build into my synthetic material, such as a constrained reaction space that utilizes entropy as a way of increasing the rate of reactions. It has proton transport pathways and channels for delivery of reactants, and that it has uniquely determined locations of multifunctional active sites so that I don't rely on simply, say, one functional site as a way of carrying out my catalytic reaction, but it's the combination of sites that make it effective. And one might think of a way of creating an inorganic hierarchical material, say, based on a MOF, for example, a metal-organic framework, that can reproduce this. And in fact, there are many groups in the world who are doing this sort of thing. And that's the science of design, knowing where to put the atoms to achieve a targeted function. It's the traditional realm of material science, structure-function relationship. But over the past 20 years, there's been an increasing focus on the other half of this problem, which is, how do I get the atoms where they need to go in order to obtain a targeted structure? I may be able to design a material, that doesn't mean I can make it. And that's the science of synthesis. Now, when it comes to crystalline materials, for a century, our view of how they formed was dominated by two theories that are based on the growth of materials by atomic addition. Now, what I mean by that is, if you're making a material from a solution, it's ions that add. If you're making it from a vapor, it's atoms. If it's a colloidal crystal, it's individual particles. And those two theories are a classical nucleation theory, which describes how ions or atoms or molecules or colloidal particles come together to form the first ordered structure. And what's unique about this regime is that it requires the system to go uphill in free energy before growth can be spontaneous. And that is, here's a nice in situ TEM movie showing the nucleation of gold particles. And in that circle, you can see a fluctuating particle that comes and goes and comes and goes, eventually disappears. And that's a reflection of the fact that, and it's one of many, that it's trying to climb up this hill before it can spontaneously grow. After the nucleation process, the next stage is, of course, growth. And our understanding of growth has been dominated by the Terrace-Ledge-Kink model of growth, which says that surfaces of crystalline materials are covered in atomic steps. And the way they advance is the attachment of atoms or ions or molecules to the step edges. And this is not a free energy diagram. This is an energy diagram, meaning that what's dominating this process is kinetics, because the free energy barrier is gone. And now what we're doing is fighting the barriers to adsorption, diffusion, and incorporation at step edges. And here's a nice example. This is a calcium oxalate monohydrate, just a crystal growing in solution. And here, because dislocations create a constant source of steps, it's where growth happens most rapidly. And at higher resolution, you can see the individual kink sites showing that this material is growing by the addition of individual molecules, not by some more complex species. Well, that's the way in which we viewed the formation of crystalline materials, and indeed, those were very successful theories for describing what would have been the functional materials of the 20th century, single crystals. And here's a beautiful example, perhaps my favorite. This is potassium dihydrogen phosphate. It's about 1 meter in size. But with the advent of the realm of nanoscience and nanotechnology, we realized that our old classical view of crystallization is just completely inadequate. The combination of nanomaterials such as nanowires and nanoparticles and nanoporous materials like zeolites and MOFs taught us that pathways can be much more complex. It's not just monomer by monomer growth, but there are a whole series, my slide won't advance, there we go, a whole series of pathways to the crystalline state involving oligomers and ion complexes, dense liquid droplets that you would normally associate with spinodal, but not within a spinodal region, amorphous particles, poorly crystalline particles, and even nanocrystals that assemble into so-called mesocrystals of individual particles that are all co-aligned through a process called oriented attachment. And that's the process that I want to focus on today. My slides don't seem to want to advance for some reason. I don't know why. I'm going to focus on this process of oriented attachment. Now, oriented attachment is a common pathway in a wide range of nanomaterial systems. It's very common in oxides. I give this example because it's the very first discovery. It was from Lee Penn and Jill Banfield back in 1998. They reported TiO2 chains where all the particles were attached on the same kinds of faces and the particles are co-aligned. Here's an example of iron oxides, aluminum oxyhydroxides, and zinc oxide, very common semiconductor oxide, grows by oriented attachment. You can see it's made up of these domains, but they're co-aligned along the 001 axis of this wire. But it's also seen in other kinds of semiconductors, here direct band gap semiconductors, lead selenide, cad sulfide. This is perhaps my favorite one. It's already made up of these very interesting nanoparticles, but they then organize themselves with certain crystallographic orientations. It's in metals. It's actually work from Yu Huang's group on platinum. And it even happens in peptide and protein systems. Individual domains will diffuse and find one another, and the crystals will grow that way. Oriented attachment is an emergent outcome of the interplay between the molecular scale structure, atomic scale structure, mesoscale forces, and macroscopic motion. So let's take a solution system, right? There is a distribution of solvent molecules and ions between particles. And as they approach, they feel forces that are mediated by that interfacial structure. But as those forces drive particles together, this structure evolves. That changes the forces, that changes the motion. And it's this evolution of structure, forces, and motion that we need to understand. Now, here's a nice TM movie we did some years ago showing aggregates of particles already formed through oriented attachment. This is an iron oxide system. And you can see this as particles drifting by, it suddenly realizes there's another particle very close, and it stops in its tracks, rotates until it's co-aligned, and then it jumps to place. Now, it doesn't have quite exact alignment at the moment of contact, so you can see it slightly rotate back again, healing the defects, the edge and screw dislocations that existed at the interface initially. But in the end, it's a perfect attachment. Now, if we want to describe this quantitatively, like we have been able to describe crystal growth using classical theories, we need a description that crosses scales to connect these molecular details of structure to the ensemble behavior via this relationship of structure to forces to motion. Now, the way that this has traditionally been viewed is in the sort of simplistic DLVO theory, where there's two dominant forces. One is a repulsive electrostatic force, which goes like 1 over R, and the other is a strongly attractive van der Waals term, which takes over at very short distance because it goes like 1 over R cubed. And the result of that is a secondary minimum, and then a barrier, and then the contact. And the ability for particles to be captured in the secondary minimum and orient themselves before overcoming this barrier is sort of the hypothesized view of how you end up with oriented attachment. Problem is that the world's far more complicated than that, and there are many complexities that aren't captured by DLVO theory that impact OA. There's the complex structure of the interfacial region, and it's largely ignored compared to the balance between van der Waals forces and electrostatics. The DLVO theory ignores the real solid solution interface. For example, there are hydration layers that are structured both perpendicularly and laterally across the surface. And that creates multiple hydration barriers and orientation-dependent minima, and it magnifies the van der Waals term. So even the basic terms in DLVO theory are altered by this interfacial solution structure. And then there are solvent and ion distributions between the opposing interfaces that are impacted by the existence of those interfaces and the solvent structuring. Those in themselves, so this is a plot, this is a calculated plot, this is not data, this is data, showing a distribution of ions between two surfaces. Those modify the solvation barriers, they produce their own ion correlation forces, and they create solute gradients that can alter the chemical potential in the system. So the outcome is a set of phenomena that's just not predictable from simple DLVO theory. The question is, how do we get to a quantitative picture of growth of nanocrystals by oriented attachment? Very strange that this doesn't want to advance. I may have to go out of laser pointer mode. So just to highlight some of these differences, I want to show you the results from molecular dynamics simulations from my collaborator, Sebastian Kiersit, of the effect of confining solution between surfaces on the solution structure and the control of surface chemistry on that. So this is the model geometry. Imagine bringing a nanoparticle down towards a surface, identical materials, identical faces, and we're simply going to look at what the distribution of water is between these surfaces as they approach one another as a function of distance and also as a function of orientation. So if we first look at the difference in water density versus distance from the surface, as for different materials, what you see is that depending on what materials we look at, these distributions are very different. So if we have magnesium oxide, which is the most hydrophilic, we have this very dense layer of water right near the interface. If we go off to pyrophyllite, which is the most hydrophobic or the least hydrophilic, we see this water peak is pushed out further and is not as intense. And in fact, if you look at the energy of pulling surfaces together or apart, you can see that it scales with the hydrophilicity. So clearly, the surface itself, in addition to the structure changing the distribution of water, the chemistry matters as well. And of course, that's not a surprise, but I just want to emphasize this point. Now, what does it do to the barriers? So if we now look at the potential of mean force for bringing particles together, we bring them towards the surface, what you see is a set of wiggles, right? And eventually a drop to a deep minimum, which is the contact. Now, if you look at the size of these wiggles, this is due to the water layer. So this is one water layer, two water layers, three. To get past these water layers, we have to go over these barriers. And these barriers are on order of 20 kT per nanometer squared. Okay, so this I think is the data for MgO. Okay, you can also see the effect of misalignment. So if the particles are perfectly aligned, they have a deep minimum and they have a sizable barrier. As you start to misalign the particles, you lose this minimum, becomes less likely that the particles will come together. And in fact, for 30 and 60, 45 degrees in this magnesium oxide system, there is no minimum, a primary minimum. But look at the heights of the barriers. This arrow is only 23 kT per nanometer squared. And that means that for a particle that's only 3 nanometers on a side, the barrier to contact is 200 kT. And so it seems like oriented attachment is virtually impossible in such systems. So the question is, how do we actually get oriented attachment? So let's look first at the zinc oxide system. And this is work from Lily Liu and Ilias Nikuzi. Zinc oxide undergoes crystallization by particle attachment. And if you look at the details of the particles, what you find is that it's dominated by oriented attachment. That is, the particles come together co-aligned, and they're always co-aligned along the 001 axis of zinc oxide. Now, if we do image analysis of this data, this is in situ TEM of particle interactions at assembly. If you analyze the position of every particle, you can create a radial distribution function, G of H, where H is a separation. And the radial distribution function looks like this. It's a smoothly increasing curve. I've blocked out this region because the problem is that once the particles get to within a couple of nanometers, they jump to contact very rapidly. And so this region is always devoid of particles. They never exist in this region. So the G of R is not valid here. But for all the data, this is the black curve is the average, and they all at all frames of the movie, they look like this. Now, we can invert this to an interaction potential because, of course, the probability of particles being in any given location is exponential in the free energy as a function of the distance from other particles. And so this is what the potential energy versus distance looks like. And what you see is, this is in KT, right? There are no barriers. It's a smooth drop to contact. And I mean, maybe there are some barriers, but within the noise in our data, they're certainly not larger than 1 KT. And so the question is, where's the disconnect between molecular dynamics and the reality of what we see in the experiments? So let's take a closer look at this. If I can get my slides to advance, there we go. First of all, we look at the individual attachment events, and we find that something very surprising, and that is that these particles feel one another and experience large torques at separations way beyond anything that molecular dynamics would predict. The MD simulations show interactions maybe out to a nanometer and nothing beyond that. But you can see these particles are separated by more than 5 nanometers, and they're already rotating into place, and they're aligned well before they come into contact. We can look at the separation versus time, and you can see even, I'm sorry, I did this in time, and in many ways it would be better if I did it in distance. But you can see the continuous attractive interaction until they get to within about a nanometer when they jump to contact. The other point I want to make is if you look at the shape evolution, what you see is the blue outline is particles before they touch. Even before they touch, now if you look at the red curve, instead of touching, these two particles have grown a neck. Now this solution is at equilibrium. We're not growing particles, but that implies that we're getting growth in this region, even though the solution is at equilibrium. And the suggestion then is that the chemical potential is somehow different with respect to zinc oxide in the gap than it is out in the bulk solution. So these are important observations that shape evolution demonstrates an increased chemical potential in the gap, and the individual trajectories reveal attractive forces and torques beyond 5 nanometers. So what's the solution here? So I'm going to cut to the chase. Well, no, I'm not going to cut to the chase. I'm going to tell you one more thing. Jin Zhang did some beautiful work in measuring the forces between zinc oxide 001 surfaces. So in order to do this, he made single crystal AFM tips out of zinc oxide using focused ion beam. And this is a TM image of the tip. Here's a SEM image showing you what this tip looks like. And the way this works is the tip is brought down to the surface. It jumps to contact, and then it becomes repulsive as the tip is pushed further. And then as you try to pull the tip off, it's stuck. So you go to a large negative force. And as you keep pulling, it pulls off of the surface. And measuring this deflection and knowing the spring constant, you can get the rupture force for pulling the two surfaces together. And we did this in an AFM with a rotational stage so that we could measure the rupture force as a function of rotation. And I don't want to get into the details of how you make sure that you're measuring the rupture force at equilibrium, which is infinitesimal pulling rate. You'll just accept that this is the equilibrium rupture force, and therefore it's equivalent to the equilibrium free energy. And what you see is a oscillatory function, which is what you expect with minima when you have alignment. Maximum in the rupture force when you have alignment, and minimum when you're misaligned. And the difference here is about 0.22 EVs per nanometer squared, which is about 20 KT for a 2 nanometer squared area. And that's the difference between being aligned and misaligned. And if you look at the molecular dynamics simulations for the same system, you find it's pretty satisfying in the sense that you also find this potential of mean force with a deep minimum for alignment and a small and smaller minimum for misalignment. And if you look at the differences in, I guess I've taken it out of here, the difference here is very close to what you see experimentally, but we run into the same problems, which is that in the zinc oxide system, we would predict that for 5 to 10 nanometer particles, the barrier is huge. Mind you, the surface area of these tips is more like 100 nanometers. And so it's impossible to push these surfaces together if these are the kinds of barriers that exist. In addition, there are no forces beyond a nanometer. All right, so the question is, what creates attractive forces and torques beyond 5 nanometers that enable the particles to approach, align, and attach? Now I'm going to cut to the chase. The answer is it's dipole-dipole interactions. So it turns out that zinc oxide has a net dipole along the 001 axis. It's not huge. It's about 670 dBi for a 2.2 nanometer particle, which is the average size of the particles, its radius particle, which is the average size of the particles in our TEM experiments. But we know that particles that have dipole moments are going to align themselves, right? And the attractive interaction is going to be like the van der Waals term. It goes like 1 over r cubed. And the torque is also going to go like 1 over r cubed. And so Greg Schenter ran Langevin dynamics simulations and looked at particles that were at large separation with dipole moments of this magnitude, and started them out at a whole range of relative orientations. You see, this axis is the relative orientation of the particle relative to a surface, and this is the separation. Started all the particles out beyond 15 nanometers. And what he found is they rapidly rotate themselves into orientation or are pulled together. Now, from these kinds of Langevin dynamic simulations, you can then produce a potential and compare it to the experimental data. And so the way he did that was to adjust the dipole moment so that the data matched the experiment at large distances. So the models simulations match the experiment. So the result of the simulation is the blue curve. It's the potential versus separation. These are the individual particle trajectories in the simulation. The purple is the data that I showed you earlier. He adjusted the dipole moment in the simulation so that the data and the model match at far distance. And the dipole moment needed to do that is very similar to what one would calculate based on literature for zinc oxide. And with that dipole moment, then you can see that the simulations closely reproduce the experiments. And so the answer is, in the zinc oxide system, what we miss in the simulations and what's really driving the system is dipole-dipole interactions. Now, it turns out that in many systems that undergo A, the situation is more complicated. And that's because often, as you know, nanomaterial systems have a phase at small size that's different from its bulk phase. And that has to do with the relative importance of surface energy versus bulk. And the second, so that's number one. So here, for example, you can see these beautiful spindles of hematite, Fe2O3, that form from actinium nanorods, which are the first particles to appear in this system. They organize themselves into these sort of football-shaped objects, but in the end, they're made of hematite. And so the question is, well, how does this work? How do you go from one phase that's, organizing itself one way into another crystalline phase that's a perfect single crystal? And the second is that you'll notice that these particles are all very similar in size and shape. And here are a couple other examples: copper oxide, titanium oxide. These are all so-called mesocrystals. That is, they are made from individual nanocrystals, but they end up being diffracting as single crystals. They're all co-aligned particles. but they all have a similar size and shape. And that's not what you would expect for a process in which particles form and diffuse randomly and attach. That ought to give you fractal shapes with a power law distribution of sizes. So there are many questions that arise about the OA process. What's the relationship between the precursor phase and the final mesocrystal? Why are shapes self-similar? What is the role of ligands? Why are there often very few primary particles present? So to look at that, we looked at an iron oxide system, hematite, that forms from a precursor called ferrihydrite, which is a poorly ordered iron oxyhydroxide. Now, in pure water, if you heat this system of ferrihydrite, it will convert to beautiful single crystals of hematite that are rhombohedral in shape. If you put sodium oxalate into the system, oxalate acts like a ligand. The hematite particles never grow beyond about 5 nanometers, and instead you get these spindle-shaped particles where all of these domains have their 001 axis along the same direction. So the long axis of the spindle is along the 001 axis. If you take preformed, beautiful hematite crystals, throw them back in with ferrihydrite and put sodium oxalate in, you get a similar result, which is a spindle. But now the particles have added on around the seed, and the 001 axis of the seed now defines the 001 axis of the spindle. And interestingly, if you measure the length to the width of added material, it has the same aspect ratio as the aspect ratio of the spindles formed without the seeds. So this is not a random process, it's deterministic. If we look at time points, these are ex situ images. We've done the same thing with cryo, and I will show you in situ TEM shortly. You can follow this process from ferrihydrite to ferrihydrite with some isolated particles of hematite, to hematite spindles surrounded by ferrihydrite, to all hematite spindles. And if you look at the length versus width for spindles of various sizes at various time points, you find that this aspect ratio is always the same. The particle sizes within the spindles all follow the same curve. The number of particles in a spindle all follow on a certain curve. And so you have to ask yourself, how do you get a deterministic process out of a random nucleation diffusion process? And you would say, well, it can't be that. So Guamin, my student, Guamin Zhu, who did this work, first he took index TEM grids. He put ferrihydrite on the grids and brought them back and forth to the reactor in the TEM and went to the same location to see what was going on. And what he found, if he fixed the ferrihydrite on the grids, is that the only place hematite could ever form was where the ferrihydrite was. And so the ferrihydrite is required either by conversion or heterogeneous nucleation to start the hematite formation. But once the hematite starts to form, the spindles grow out from the ferrihydrite into the surrounding ferrihydrite-free solution. So you can see these are half spindles now. All of them are half spindles. They point out into solution. Here's the boundary. And that means the particles of hematite are adding onto the spindle from out in a solution where there are no particles. That implies that the ferrihydrite is not adding on to the spindles, even though they must start there. But it's being replaced by hematite that forms out here and adds on, but somehow in a deterministic process. And so in order to see exactly what was going on, we were able to do in situ TEM at temperature at 80 degrees using hematite seeds. And now you can see what happens. And what happens is, in the presence of sodium oxalate and ferrihydrite dissolves away. It's just a source of ions. But new hematite particles form. They don't form out in bulk solution. They only form near the interface, and then they jump to the surface and become part of the particle. You can see that happening here. There's a nucleation event and attachment. Here's another nucleation event and attachment. Here's another set of seeds. You can see the numerous particles forming around them and then attaching. And here's a set of time-lapse images over a much longer period of time where the shutter is closed. It's opened later for some period of time, closed again. And you can see how these seeds then develop into spindles through this process. So all the existence of the interface changes the local chemistry in a way that drives all nucleation to happen near the interface, and the particles then attach to the surface. To show this schematically, without oxalate, somewhere hematite nucleates, the ferrihydride dissolves away as the crystal of hematite grows through classical ion-by-ion growth to give beautiful single crystals. If you add sodium oxalate, as soon as a hematite particle forms, oxalate covers it. It can't grow larger, but it changes the local chemistry so that now hematite particles start nucleating around the existing one and start adding on. And apparently they nucleate more rapidly along the 001 axis than they do along other directions. And so instead of spherical, they're spindles. So why does this happen? So if we do molecular simulations, and we've also done measurements, you find that oxalate covers hematite very effectively on any surface that we measure or simulate. And it's different on different faces. So there's a different surface charge on the different faces. If you look at the excess iron concentration versus distance, what you find is a maximum in iron 3+ concentration about a nanometer away from the interface. And that maximum is different for the different faces of hematite. So we know the chemistry is different. Now, I don't want to imply that the chemical potential of iron 3+ in the bulk solution is different from the interfacial region. That should not be the case. It ought to equilibrate itself. But the chemical potential relative to hematite is different. And that can result in two things. So if we look at the nucleation rate, it's exponential in the free energy barrier, and it's linear in the concentration to the second power, or goes as a concentration to the second power. The free energy barrier itself scales with two important terms. One is a cube of interfacial free energy, and the second is the quadratic term in the square of the supersaturation. Now, we don't have, this term can't change nucleation rates very much because it's only a quadratic, but you only have to change these terms by a little bit to get a huge change in nucleation rates. Out in the bulk solution, this barrier is 80 kT. So nucleation is a rare event. But if we drop the interfacial free energy by just 5%, this nucleation rate goes up by 3 times 10 to the 8th times. It's incredibly sensitive. So the difference in interfacial chemistry may be changing the interfacial free energy, or maybe the solubility of hematite is altered there and the supersaturation changes. Just a 10% change gives us a 20,000 factor of 20,000 increase in nucleation rate. We don't know which it is, but presumably this is driving one of these two changes. And once those particles form, you can ask, what is the barrier to attachment? And the answer is there isn't one. They're forming in the 1 to 2 nanometer range, and what the simulations show is it's an attractive interaction directly to the surface. They're strongly pulled to the surface, and that's the way in which these form. All right, what these two studies show you is that really we have to understand what the interfacial chemistry and structure is all about. And the question is how to do that. There are computational tools, but there are very few experimental tools. X-ray reflectivity and neutron scattering give us some information. They don't tell us much about the lateral variation or the forces themselves. Let me just skip this slide. It's not important. And so in order to look at that, we have started using AFM in the fast force mapping mode to examine interfacial solvent structure between surfaces. Now, the way this works is either an amplitude modulated or frequency modulated mode. The AFM cantilever is oscillated up and down as it moves across the surface, and one measures the shift in frequency or amplitude or phase, or feeds back on amplitude or frequency and measures the voltage needed to keep it constant, and you can measure the phase shift. And the back here is actually a map then of the force gradient seen above the surface, but I'll get into that in more detail in a minute. This is a plot of the force gradient versus distance that the cantilever sees. This is a 2 angstrom scale bar. And what you see is a typical pattern, which is a decreasing value. And that is a reflective of a repulsive term between the tip and the surface that has to do with nanohydrodynamics, sort of a competition between nanohydrodynamics and van der Waals attraction. But on top of that repulsive term, you see these wiggles. And those wiggles represent the hydration structure. And these have been classified into different colors representing the different families of curves that are reflective of the different types of lattice sites on the surface. This surface happens to be aluminum oxyhydroxide or boehmite. Let's now, if we take all of those curves, we can reconstruct a three-dimensional plot then of the solution above the surface. And that's what you see here. You're looking at a vertical cut right now as we go across the surface. The bright areas are low density, the dark areas are high density. And now we're up in the bulk. And this has the background in it. If we then subtract out the background, we get this truly amazing detailed map of hydration structure. It's really just mind-boggling that it's possible to map this out. And so this is a lattice resolution map of where the water is. Now, of course, it's not where the water is, it's the force gradient. And the question is, how is that related to solution structure? So the idea is something called the solvent tip approximation, which says that the tip acts like a solvent molecule. And the places where you see minima in force gradient are the places where there's a maximum in solvent density. So this is coming up from the surface, and there are places where the solvent is high density and places where it's low density. Again, blue is high, yellow is low. As we go across the surface, you can see this oscillating pattern. That's because we're going up over OH groups, down into cavities next to oxygen sites, and so on. If we plot the 1D force gradient curves, you can see where these minima and maxima are. And where the minima in force gradient are, so let's take the first hydration layer, they lie over the cavity sites and the oxygen sites. So that's along this row. And that is where the water can hydrogen bond to the OHs. So that makes a lot of sense, right? Now, the question is it really that simple? Is it just about is the tip really just like a solvent molecule? And the answer is no, it's not. So we did simulations. This is Sebastian Kirsitz's work again, using a silicon nanoparticle against a boehmite surface. The silicon nanoparticle represents the oxidized silicon tip of the AFM. And what we found is that if you look at the first hydration layer, it's actually the hydroxyl groups on the silicon nanoparticle interacting with the hydroxyl groups on the surface that define the first maxima or minima. Let's see, have I said that right? The OH groups position the OH groups position the first water layer are hydrogen bonding directly to the OHs, the boehmite, just like in our experiments. But when you go to the second hydration layer, he says, there, what you now find is that what we're measuring is the hydroxyl groups interacting with the water molecules in the first layer. So it's a complicated story. So if you look at the predicted density of water relative to bulk versus height, now the peaks in water density ought to be where the minima and force gradients are. And indeed, the dots are where our minima are. And you see we have an agreement in the first water layer. And out in the fourth water layer, you can see, yes, we predict a high density over all sites. In between, it's kind of a mixed bag. We get some agreement and some disagreement. All right, so surface chemistry matters. So what that tells us is we have to use the same chemistry as the material we care about. And so we're now making single crystal tips of the same material that we want to measure with. And here's a beautiful zinc oxide tip. You can see this is the bump on the end. It's a sputter deposited zinc oxide on a commercial silicon cantilever AFM tip. And this is preliminary, initial data showing that we can measure the force gradient versus distance, and we can see the differences between different solvents. We get an attractive interaction in water. We get a repulsive interaction, ethanol. They have different dielectric constants, so we expect very different dipole interactions. So we're pretty excited about being able to do this now. So I want to end now with a set of challenges rather than conclusions. Our challenge is to understand the collective outcome of this three-way interaction between solvent, surface, and solutes. How does surface chemistry and symmetry elements of the underlying substrate imprint on the overlying solvent? How does the solution structure and corresponding thermodynamic properties evolve as surfaces approach one another and begin to interact? And how do we deconvolve specific interactions between chemical moieties, electrostatics, and van der Waals forces, and the entropic terms associated with the solvent? So with that, I want to thank you for your attention. I've tried to acknowledge the people who did the heavy lifting as we went along. But I want to thank Department of Energy, Basic Energy Sciences for the support of this work and you for your attention.
Thank you very much, Jim. A fantastic talk. Your talks never cease to amaze me. So we do have a couple of questions from the audience. I'll fire away with that. I think the first question is from, let me see here. From Sherry Ren, I believe it's related to when you're talking about the spindle, the spindle formation of the iron hydroxides. The question is there any surfactant used in this system? That's from the YouTube platform.
Yes, that's if you do not put oxalate in, you will not get those spindles in the iron oxide system. If you put in citrate, you will get spherical aggregates. And so the ligand matters. And I think this is important because, of course, there are not many nanomaterial systems where ligands are not part of the picture. So what the ligands are doing is an important question. And it's actually a direction that our research is now going in, to systematically vary ligand chemistry to understand its role in altering interfacial structure in chemistry and changing the forces that drive particles together.
That's great. And there's another online question. So for those in the room, feel free to unmute after this question. So this is from Nat Deppert, Lung University. He says it's very interesting with the forces between the nanoparticles. In the aerosol phase, that's for particles in a gas, we have a rule of thumb that the attractive forces are strong enough at the distance of the diameter in order for two particles to attach to each other. I think it's more of a comment, possibly, instead of question.
Yeah, so in solution, of course, it's very different, right? Because almost all particles carry a surface charge. And even those that don't, they have a specific kind, they have an interaction with water, either repulsive or attractive. And so you've got, especially in the case where surfaces are charged, you get a distribution of ions, and those distributions ripple out, right? You've got a double layer, and then you've got ion correlation forces, especially for divalent, trivalent ions. Certain forces are screened. So it's not, there is no simple rule of thumb. You might say, what about the Debye length? But the Debye length is only capturing a small part of it.
So thank you, Jim. Any other questions from the audience here in the Zoom room? So if not, let me take the opportunity. It's great work. Answer actually a lot of our questions. A lot of our questions during our studies. So I'm just wondering, Jim, have you introduced different ionic strengths to your solution and observe how the interactions might have changed?
So right now, we've varied the ionic strength in the fast force mapping experiments over a very wide range, and we're in process of writing up some of that data. And we've done that for mica. Mica is supposed to be the model surface, right? It turns out it's a nightmare surface. I'm sure that when Wolfgang Pauli, said, God made the bulk, but the devil made the surface, he was talking about mica. But anyway, I digress. So we've looked at ionic strength in those measurements. In the in situ TM experiments for OA, we're really focusing on zinc oxide and TiO2 and hematite, and we haven't been varying ionic strength. That's next. But what I do want to say is for the zinc oxide, we've been varying dielectric constant. So the data I showed you was for methanol. It turns out water doesn't work, unfortunately, in the TM because the particles all stick to the membrane, so we can't do water. But we've done toluene, and we're doing we're using cryo-EM to look at water because water is 80, right? So we'll have 80, 20, and 5. And so because we say the dipole-dipole interaction is dominant, that's the thing that ought to vary the dipole-dipole interaction, right? Not the ionic strength. So that's what we're playing with right now. hopefully in a few years, I can tell you the effect of ionic strength in the hematite and the TiO2 systems.
Great, thank you. I
Well,
look forward to those results.
if
I see
I'm
Yuri.
allowed, right, yeah, I would also like to ask a question, even though I missed much of your talk, Jim, because of my presentation. But in MXenes, we deal with very similar issues that you described, water at or between the layers, and we're trying to understand the structure of this water in confinement. And what I'm wondering, whether you looked at the effect of protons or hydronium ions or other ions on ordering of water and interaction of water with, say, titanium surface, which is to a certain extent very similar to titanium carbide MXene, the same TiO or TOH bonds on the surface.
Yeah, so the TiO2 work is really in its just beginning. So I don't have anything to say about that. We have varied the pH over a large range for the boehmite system and the mica system. And there in our, the simulations tell us about the hydronium ions to the extent that we can trust the molecular dynamics simulations to get that right, or the DFT, in the case of the mica, the DFT simulations, then we can say something about that. But in terms of what it's doing to the forces, I guess I don't have any comment on that. What it's doing to the structure is quite important. It does have an impact, a significant impact on water structure, yes, at least in the mica case.
We observe it too, but it's not an easy task.
No, it's not.
We're trying to understand what's going on by using a variety of techniques.
I think, honestly, one of the biggest challenges here is, the number of tools for looking at a surface or at a bulk is rather large, but the number of tools for looking away from the surface, knowing where the ions and atoms are, in the liquid, they're just pitifully small, right? X-ray reflectivity gives you sort of an average picture. It's an excellent picture. It tells you about the laterals, the longitudinal structuring that is away from the surface. But about the atomic scale distributions, especially lateral, you don't get that. And, so you have to start, now you have to ask yourself, well, how do I trust my simulations? And that's part of our hope with the fast force mapping is you ought to be able to predict that, right? That's now a probe with atomic scale sensitivity. And so if we can't, and it's directly measuring a potential amine force, so we ought to be able to predict that correctly and then trust the simulations.
We work with Paul Fenter at Argonne National Lab on X-ray reflectivity.
Oh, yeah. There you go, yeah.
Right here. So we use pretty much the same techniques. Yeah.
And so do we. So everybody does.
Thank you.
Let's take, thank you, Jim. Let's take a final question if there's one, and then we'll move on to Yuri's talk. If not.
So, Jim, it's a great talk. I actually want to continue on Yuri's question on a different material. So, basically, I'm curious whether you could probe, for example, water and the platinum surface interaction at different electrochemical potential.
Oh, yeah.
Or different pH.
Yeah, absolutely. No reason why we can't do that.
So
I mean, we're doing a lot right now with applying electric fields and looking at the effective forces, and it's definitely doable.
Okay, that'd be great. That'd be great if we actually have an ongoing study. Probably we can talk later. Maybe that can help us to get some
we should follow
evidence.
up later on this.
I mean, we've applied this technique now to even very different kinds of materials, including layers of proteins and synthetic, sequence-defined polymers like peptides. Yeah, I mean, it's generally applicable. The challenge is the interpretation, right? You're measuring force gradient. You need to convince yourself that you know what that means. In some cases, it's simple, but if chemical interactions are involved, it's not.
Great, thank you.
Thanks again, Jim, for a great talk. Right. So let's now move on to Yuri. Yuri's here. Professor Yuri Gogoshi is our second speaker today. Yuri is the director for the A.J. Drexel Nanomaterials Institute, and he is the Distinguished University Professor and Charles T. and Ruth M. Batch Professor of Material Science and Engineering at Drexel University. He received his bachelor's and master's degree and also PhD degree from the Key Polytechnic and also a Doctor of Science degree from the Ukrainian Academy of Science. Yuri is well known for his seminal work on the 2D carbide and nitride, or the MXenes, which he discovered with his students and collaborators. So he has shown that this unique class of material has very a wide range of applications, and this class of material has quickly expanded and demonstrated their applications in energy, environmental protection, electronics, and medicine with the efforts from him and his group. And Yuri has certainly received a long list of recognitions for his seminal contributions to the material science. But for the sake of time, I'll spare most. I would like to point out that the most recent award that Yuri have received is the MRS Serbia Award, to recognize his lasting and outstanding contribution to material science and engineering. And today we'll hear from Yuri all about the journey of discovery and development of MXenes. So Yuri, the stage is all yours.
Thank you very much for your introduction. It's a pleasure to speak to you about our research in MXenes. And MXenes, for people who are not familiar, are those structures that you can see schematically shown on my front slide. So red dots stand for transition metal, and black dots connecting those red spheres are carbon or nitrogen. So it's basically carbides and nitrides of earlier transition metals, made in a two-dimensional state here. So why are they important? There is a lot of attention to 2D materials. In the morning session, first plenary session today, there have been 4 talks. All of them discussed graphene and graphene-related materials, plus 2D diamond and some dichalcogenides. And really, discovery of interesting physics in graphene led to attention to a variety of other two-dimensional materials that can be initially like graphite, produced by separating layers, say in boron nitride, hexagonal boron nitride, which is isostructural to graphite, or transition metal dichalcogenides, which again have layered precursors, or also clays, like you have heard about boehmite clay, where there are 2D layers as well. And clays are among the most used tonnage-wise nanomaterials and composites here. However, this interest also led to discovery of new materials like silicene, germanium, phosphorine, materials for which there were no layered precursors available here. And clearly, the interest to 2D materials and their unusual electronic properties, which range from metallic to insulating, semiconducting, flexibility and optical transparency, which are required for making wearable devices, for making basically devices for Internet of Things and wearable Internet. Plus, in additionally, high surface area that gives opportunity to give basically these materials, jumped ahead, I think, surfaces that can be used, for example, for electrocatalysis, for electrochemical energy storage, other processes. Those are unique because in those materials, the entire material is the surface here. So MXenes actually played an interesting role here. They are the most like a metallic of available freestanding two-dimensional material things here. So when we discovered them, we not only like really played the opening game for a very large family of materials, and I will convince you later that we can have at least 1,000 of well-defined chemically defined structures plus infinite number of solid solutions with very interesting properties. But also they added something that was really missing in the 2D materials world. They added truly metallic materials with a high density of states at the Fermi level, with a high concentration of carriers to the world of 2D materials, which are mainly semiconductors, dielectric, or semimetals. Recall that even famous graphene as a zero band gap semiconductor here, even though it's praised for its high conductivity in many cases. So what is really happening in the world of nanoscale materials, first of all, two-dimensional materials? We're moving from working and developing like a single material, like a graphene, which is important, very interesting, lots of new interesting physics and already some application emerging, to the future when we will be able to assemble new materials and entire devices by using 2D sheets as building blocks, like a bricks building a wall or Lego blocks. So pretty much we can build structures and material with properties not available today. Moreover, we need for this naturally dielectric, semiconducting materials, and metallic materials. We need materials with different surface chemistries, with different properties here. So that's extremely important because we can make anisotropic structures. We can design and produce devices without waste, just simply by assembling them, chemical assembly, self-assembly here. And of course, we can also assemble 2D sheets with zero one-dimensional materials. But one thing is important here. 2D sheets can be assembled in a very dense way, producing really something looking like a perfect structure, like, again, bricks in the wall, without gaps, with a high density. And that's actually important for many applications. Let me just go back to MXNs and explain a little bit better what those materials are. I already mentioned the carbides and nitrides. So golden spheres here in this schematic represent transition metal atoms. Black dots are carbons or nitrogens, or recently it was shown that you can also make 2D borides, so potentially can be boron as well. They're few atoms thick, sub-nanometer thickness usually, just like other two-dimensional materials here. But what is very, very important, most of them studied so far are metallic conductors. And in this structure, you have a conducting carbide core. So electrons of transition metal in this layer provide high metallic conductivity. And the outer layer actually show here terminating by OH groups, just like you would see it on the surface of silicon oxides, as you could see it in previous talk by Jim Yuri, which gives actually hydrophilicity to this material. So first, right away, you see unusual thing about these materials here. They are like a hydrophilic water-soluble metals. Moreover, you can actually change the surface chemistry of this material, and you still can keep their conductivity. Unlike, say, graphene, when you transition to graphene oxide, described by Rick Kenner and others today, you basically kill the conductivity completely. Moreover, this transition metal oxide surfaces can also change the oxidation state, transition metal atoms. And you can basically use it for energy storage or other processes here. And they come in a variety of flavors. So you can have materials with 2 layers of transition metal, 3, 4. We call them 2-1, 3-2, 4-3 structures. They can have a variety of elements on M side. So M in MXN stand for transition metal, X for carbon nitrogen, and we pronounce it MXNs for just easy pronunciation, like a lady's name. Titanium-332 was the first one discovered in our lab by Michael Nagib, who was a PhD student working with Professor Michel Barzoum and myself. This is the first paper, which was published in September 2011. even though the material first sample was produced earlier. And actually, Advanced Materials is publishing now, and it should be online very soon, a virtual issue on MXene to commemorate 10 years of MXene discovery. This picture will be on the cover of this issue, but the paper itself, actually, our editorial, written with Michael Nagib and Michelle Barzoum, is already available online. So you can read about progress in MXene field and growth of these things here. There are more than 1,000 organizations from many countries working, publishing MXene. Last year, we had a conference which went virtual because of the pandemic at Drexel University, with more than 2,000 registered participants from 63 countries, more than 750 institutions. So it shows that its entire field has been formed. Actually, just a couple of days ago, a bibliometric analysis of MXene field appeared. So people who are in like a library science feel that the field is formed and the number of publication is becoming very large here. So it's a fun, but why? Why do we care about making more materials, new materials here? It's not just necessary to have many building blocks. Yes, you want to have Lego stones of all sizes and all colors if you build something. But in materials, you also need specific properties. And this is an example of calculated density of state. For example, for one of the simplest and actually one of the first discovered titanium 2C MXene, you can see that there is a high density of states at the Fermi level when there is no termination. But typically, we get MXene with surface termination, oxygen, fluorine, OH, and you see fluorine termination significantly affects density of state, and oxygen termination can also potentially open a band gap. So what is important? We have metals where change in surface termination, we actually tune the Fermi level. So there are metals which are two-dimensional, water-soluble, and with a tunable Fermi level. And we can do it reversibly, chemically or electrochemically, for example, by injecting charges here. Moreover, it's not only transition metal or carbon or nitrogen that control the properties. Surface terminations also affect significantly many properties, from magnetic properties to, as it was shown by Dmitry Talapin in his science article last August, just exactly a year ago it was published, also superconductivity. Niobium 2C with selenium or sulfur termination becomes superconductor, while oxygen terminations, for example, kill superconductivity. Now, what do we have today? 10 years after this first discovery of titanium 332 MXene. We have a large number of structures: M2X, M3X2, M4X3, M5X4. So actually, those are the thickest two-dimensional materials. Each of these blocks, which is just a little bit thicker than nanometer, is well-defined, has exactly the same composition, same thickness. But say, unlike graphene, which is flimsy, those are rigid. Bending rigidity is actually orders of magnitude higher than graphene. So you can construct very thin devices, self-supported films here. We have also materials which actually are atomic sandwiches. We can have one transition metal on the surface and other transition metal in the middle, where the chemical and electrochemical, catalytic, other properties of the surface will be determined by the transition metal on the surface, for example, moly. And electronic and transport properties will largely be determined by the transition metal in the middle, like titanium. And it's also possible to go further in atomistic design. It's possible to make materials with not only out of plane, but also in plane ordering of elements, which are alternating columns of different metals. For example, yttrium and tungsten, scandium and molybdenum. So they're called iMXene or in-plane MXene, ordered MXenes. And it's not over. We can etch away one of those elements, for example, yttrium or scandium, and leave vacancies, monatomic, basically, columns on vacancy, divergences on the surface, making materials with this type of open surface structure. So you get the idea. Sky is the limit here. Moreover, if you look at about 10 different transition metals used, carbon and nitrogen, you end up with possible like 100+ combinations that you can design the structure. If you multiply it by about 10 different surface terminations demonstrated so far, you have about 1,000 well-defined structures. But now you can make solid solution on M side and solid solution on X side. And recently, this year, already 3 research groups have demonstrated high entropy multi-elemental MXenes. So basically, we have a family of materials which promises to become possibly the largest known family of materials in general, and definitely the largest one in the two-dimensional world. So far, more than 30 stoichiometric compositions, again, as I mentioned, dozens of terminations, and also probably about 20 different solid solution and multi-element high entropy MXenes have been reported. So we're still in the beginning. There is plenty of room for synthesis. Many more carbides and nitrides have been reported. Also, so far, most of MXenes have been produced by etching, selective etching, a element from so-known MAX phases, and this is actually how the name MXene came from. So A stands for one of those elements like aluminum, silicon, gallium are the ones typically being etched here. There are also layered carbides, for example, aluminum zirconium carbide, hafnium aluminum carbide, and you can etch the entire aluminum carbide layer away. So, but you need layered precursors. One of the goals is to also make MXenes from elements that we won't depend on availability of precursors, which actually limits the number of MXenes we can make today, as we need to make first the precursors. But what is also important to mention here, when you do synthesis of MXenes, you cannot just take this layer structure and easily exfoliate it, as it is done in the case of, say, graphite or molybdisulfide or vermiculite clay. There are strong metallic or covalent bonds between a element or carbide layer in the structure of layered precursor and carbide or nitride layers, which would form MXene. So we have to selectively etch it. Just like we etched in the past, for example, transition metals from carbides to make porous carbon or graphene-like carbons, or as people etched, for example, silicon from silicon carbide to make graphene and vacuum. Same way we need to chemically remove it here. So this is what brings this surface termination. Typically it's oxygen OH. If etching is done in aqueous environment, can be halogens. If etching done in, for example, molten halide salts, you can get chlorine or bromine on the surface here. There are many other methods now that have been reported using halogens in organic solution, gaseous halogens using electrochemical hydrothermal etching. But basically, we're looking at family of materials produced by chemical processing like graphene oxide. It has its limitations. We may not get absolutely perfect and ideal particles. We get surface termination, but there are also big advantages. If you look at majority, great majority of two-dimensional materials and nanomaterials in general, most of them, and there are like a couple of hundred 2D materials already, like more than 200 reported, are produced in micrograms quantities, milligrams, grams. Two-dimensional boron, two-dimensional gallium arsenides, gallium nitride have been produced basically as monolayers, need protection, not to degrade, and their application may be limited to sensor electronics, something with a very small amount of material required here. If we want to move towards biomedical application, conducting inks, electromagnetic shielding, catalysis, and of course, even more to like a large-scale energy storage or generation or construction materials, we need much more. And here, actually, graphene, clays, moly disulfide, tungsten disulfide, boron nitrides form a very, very small group of materials where significant amounts can be produced. What is important? Because of this, MXene synthesis by chemical etching of ceramic powders, basically like max phases, we were able to make grams of materials from pretty much day one. We can make up to 100 grams in a run in the reactors that we have in the laboratory now, which were designed for us by MRC. And there are kilogram size reactor in industry. So it's an intrinsically scalable process. And you can basically take the material of the synthesis and washing, and you can often directly process it into a film. So we start with ceramic powder, like you see one here. Those are titanium 3C2, for example, layer. You only see titanium, you cannot see carbon here, connected by monatomic layer of aluminum. You etched aluminum away, say in hydrofluoric acid or lithium fluoride HCl solution, and you can see that the surface becomes terminated now, and aluminum is gone, but the layers of titanium 3C2 did not change. After that, you can exfoliate it by intercalating, just like you'd be exfoliating many other two-dimensional materials, because now there are weak hydrogen on van der Waals bonds between the layers, and get these single layer flakes. One more important thing to mention here. You can find flakes which will be microns or even tens of microns made of graphene boron nitride. Even for moly disulfide, I've not seen solution processed flakes larger than a micron because this material are not strong enough. We can do solution processes and still get 10, 20 microns flake of these materials. Moreover, what is nice, you take it, powder, delaminate it, make this colloidal solution. This is a 1 liter bottle with probably like a 10, 20 milligram per milliliter solution. You can concentrate it, you can make liquid crystalline solution, you can filter it into a film, or you can choose that Dr. blading and produce without any binders, any additives, films which actually has mechanical strength of higher than aluminum foil and conductivity of say 15 to 20,000 Siemens per centimeter. So what is important? We can process all these materials just from water, no surfactant or binder added. So if we do, for example, inkjet printing or spray coating, spin coating as a technique, unlike say metal nanowire, something else, we don't need surfactant. We don't need to burn binder and surfactant after producing the film. We just get natural adhesion between those layers. Moreover, since those are two-dimensional sheets, that can be just a graphene oxide, say, form liquid crystal. And we can produce films. We can also even pull fibers from a liquid crystalline MXene, making pure MXene fiber. There are probably 5 meters, if I recall correctly, on this pool of titanium 3C2 fiber, which is again just MXene. This is an SEM image showing the surface of this fiber here. So basically, we get a large variety of two-dimensional materials, couple of atoms in thickness up to, say, 9 atoms so far, 6 that we can make distinctly here. The key properties are high metallic electrical conductivity for majority of them. This is, for example, a multi-layer film of titanium 3C2. And I know Rick Kenner showed a film, a multi-layer film of graphene or graphene oxide, which looked exactly the same actually. So there are similarities. This is a single layer flakes produced basically just separated by filtration on substrate. And you can see TM images of flakes, which actually repeats crystallography of the max phase precursor. But what is important here, you see like this flakes is hanging in a hole, and graphene would not be able to support itself. but MXene is much more rigid, it does. But if you look at the high resolution TM image or electron diffraction, you will see those flakes are single crystal. So a single layer, single crystalline materials here, but with very high mechanical strength and stiffness inherited from transition metal carbides, nitrides. Of course, they are, as I mentioned already, hydrophilic, soluble in water. So just by combination of these properties, it already gives many interesting advantages for applications. But also, they provide a variety of colors because they have plasmonic properties here. You have seen MXene solutions and film of several colors on the front slide when I showed you initially here. And of course, you can control it by controlling the composition. Those are UV spectra you can see here. And this goes actually to now IR to about 2.5 microns. And you can see that there are all these absorption peaks, which are plasmon resonance, transverse surface plasmons, which are controlled just by the thickness of this material. So lateral dimensions don't affect the position of those peaks here. And some MXenes are transparent in IR, some absorb strongly in IR. So we have materials with just basically variety of optical properties. And they're also very strong. They are strongest of solution processes materials. Ideal boron nitride graphene separated from the crystals, couple of CVD grown materials may have a high mechanical strength, but they're strong and they say reducing graphene oxide or graphene oxide here. So what is important? We need to look at this complex of properties to understand where the applications could be. And again, one of the key things here, those properties are tunable. A message I would like to leave you with. You have a family of materials where you don't take what is given to you by nature and work with it and try to find where it fits. You select, design, predict computationally, make experimentally, and use material for application where you can tune all those properties here. And let me just give you one example, which is easy to visualize. So you see here 3 different MXenes, titanium 3C2, titanium 2C, and V2C. Titanium 3C2 has transverse surface plasmon at about 780 nanometers here. And if you change transition metal from titanium, from basically thickness of the layer, from titanium 3C to titanium 2C, make it thinner, you shift it. And the surface plasmon of titanium 2C will be at about 550 nanometers. So you change the color in transmission from green to red or reddish, but in reflection, those will be complementing colors. So titanium 2C actually will be green and titanium 3C2 will be kind of violet here. And V2C, when you change transition metal, actually will have a surface plasmon in the UV range. And one of the classical examples, everyone gives giving talks to general audience on high school kids about nanotechnology and this Lycurgus cup from the 4th century, which contained gold or silver particles, making plasmonic this glass. And as a result, it looks red in transmission and green in reflection, just like titanium 2C MXene, which unlike this cup doesn't have noble metals. So you can use plasmonic properties in a variety of plasmonic optoelectronic application. You can use MXenes as substrate for surface enhanced Raman spectroscopy, for example, instead of gold and silver. So again, keep in mind, many cases when we work with MXene, we are actually replacing gold in many applications here. And of course, variety of properties lead to a range of different applications. I won't have time to go in details today, of course, but I will just give you some flavor, give you some examples, how based on properties of MXenes, we can use them in various applications, ranging from energy storage This is probably the most studied ones. MXenes have been used in a very wide variety, or explored at least for a wide variety, from supercapacitors you have heard a lot about today in Professor Kenner's talk, to printed electronics similar to graphene, but application may be somewhat different, or sensors, again, you have heard about today, to electromagnetic interference shielding, because MXenes interact with electromagnetic radiation in a very broad range, from UV to radio waves. And of course, there are medical applications, because titanium carbide, tantalum carbide, a number of other MXenes have been shown to be biocompatible, blood compatible, non-cytotoxic. And also, because MXenes can be produced in larger quantities, they have potential in environmental and larger scale energy storage applications. But let us just go through a few examples here. I already showed you, for example, variety of optical properties combined with conductivity going to 10-20,000 Siemens per centimeter. And one, of course, obvious applications for two-dimensional material here is in transparent electronic. For example, replacing indium tin oxide in organic OLEDs, light-emitting diodes. And you can see that pretty much performance, which is shown here for titanium 332 MXene film and ITO, is largely analogous. This is a work with Korean collaborators. But unlike ITO, you can produce it on surface just from aqueous solution, spin coating, spray coating, self-assembling, deep coating on the surface, and the film is flexible. So you can basically flex it, you can bend it, you can actually twist or fold it, and it will still maintain its conductivity and won't crack, unlike NTO. Printing, conducting substrates, current collectors, again to replace gold, replace other metals, and do it at basically from aqueous solution, or actually you can dissolve MXene or disperse MXene, make colloidal solution and polar organic solvents as well. Also becomes a popular topic here. Of course, they can be incorporated in aerogels. This is a work from Kaust showing excellent stretchability of MXene aerogels. And there are dozens of papers already on use them for soft robotics, strain and pressure sensing here. So soft and hard robots, electrochemical actuators, photoelectrochemicals or actuators have been demonstrated with MXenes here. So those are just a few applications that are emerging here. But the number grows very quickly. Hussam Al-Sharif from Kaust predicted that a new field is emerging. He gave a name to it, Maxtronics, because of this variety of compositions, structures, and properties. Variety of functional group that you can get. You can also intercalate them to further modifying the properties. Surface charge, actually majority of MXene after synthesis have a high negative surface charge between -30, -80 millivolt, what makes them soluble here. These optical responses, tunable band structure, and also work function, which depend largely on the surface termination, has been predicted to go from 2 to 8 electron volt, depending on surface termination and MXene compositions, and variety of electronic, magnetic, plasmonic properties resulting of it here lead really to possibility to create entire fields of electronic, where MXenes can also work as current collectors. We recently showed also with Alex Sinitsky that have a very high breakdown current at the 10 to the 8 amperes per centimeter level, very similar to graphene. So you basically can build variety of different devices. One of the very interesting applications for MXene appear to be electromagnetic interference shielding and communication. As we have electronic devices 5G, 6G, internet. We have lots of Internet of Things devices around us. Shielding them and protecting them from noise, from crosstalk, as well as protecting devices on the same chip or on the same cell phone from crosstalk, becomes a very big issue. Traditionally, metal grids were used or metal foils, but they're heavy, bulky, and we showed in an article in Science in 2016 that titanium 332 MaxSyn actually lines up with much more conducting metals like aluminum and copper. And since we can produce freestanding films going down to 1 micron, and this film can provide about 50 decibel, so it means that 99.999% of waves in X band will be reflected or absorbed here. So we can make much thinner shields for electronics. But last year, a year ago, actually, as the August 2020 issue of Science, we showed that titanium 3CM, which is actually thinner, which is actually less conducting than titanium 332, and traditionally it's considered that conductivity is the key issues for here, for shielding, outperforms metals like copper. So what it shows that there is interesting new physics. When the waves interact discretely with all this layer of the materials and get basically absorbed or reflected more efficiently than in metals. And this actually has been truly a breakthrough in the field. One interesting fact to mention, before our 2016 paper with Chongmin Ku from KIST reporting on titanium 332, there have never been a paper on electromagnetic interference shielding published in top like a high impact journal like Science or Nature, just because not much happened in the field. Within 5 years, this first paper became the most cited paper in EMI shielding field ever, and the already license has been sold to our company, and there are also already basically products in development. But you can use them for other applications. You can use them for communication. You can again make antennas which will be as efficient as copper antennas by about 10 times lighter and thinner than copper, and you can again print them on a variety of surfaces. You can make flexible antennas or even like a neat antennas here and get radiation efficiency lining up again with copper, but and again at much smaller thickness here. So I hope it gives you some of the ideas of applications here. And of course, energy storage is a topic that my research group has been targeting for a long time. You have seen an earlier version of this plot from our 208 paper in Professor Kenner's presentation today. We published last year an updated version showing progress in the field of electrochemical capacitor and batteries here. But the target that you saw today is still remaining. Everyone wants to have a battery charging within 5 to 10 minutes for the car or cell phone. Elon Musk promised this to happen. And actually then the mileage limit will become less significant if you can charge your car within minutes and don't have to wait for an hour. You don't necessarily need a 500-mile battery. But getting there is not easy because this Ragone plot shows you specific energy, which defines how far you can go, and specific power, which defines how fast you basically can charge, discharge, or well accelerate, is a log-log scale. So getting to this point of, say, minutes charge and discharge is not easy. It's like an order of magnitude increase in power. And getting from the energy density of supercapacitor is even more challenging because there are a couple of order of magnitudes energy density needed here. So how can we get there? What do we need from materials to get there? We need materials which have some redox because pure double layer capacitance won't probably be sufficient to achieve energy density level of current batteries. But we need materials that charge quickly. For it means we cannot afford solid state diffusion. We need to have surface charge processes. And this is what requires low dimensional nanomaterials. But moreover, what does it mean charging something quickly? It simply means running a very high current through the device. You know what happens if you have a poor conductor and you try to run high current through it? It heats up. So we need materials with much higher conductivity. And this is what MXenes can potentially offer. They have metallic conductivity, which is like an order of magnitude higher than reduced graphene oxide. But they have transition metal on the surface that can change its oxidation state. And they have channels between the layers where ions can move in aqueous or non-aqueous electrolytes here. So that's potentially why MXenes are so attractive for energy storage application, whether we're talking about larger scale devices, but first of all for micro scale, printable on chip or wearable devices. Here, very similar to graphene, where it can compete in those applications here. Of course, there are many other applications, but I think even my extended time is coming to the end so that we can finish within a reasonable time here. So you can use your imagination. And again, what is important? In our group, we built all our application or device design on basic fundamental science, on understanding properties. Because if you understand material properties, if you can get properties that you need, you can develop the applications. And a good example or couple of examples to show is here. Gas sensing. So usually semiconducting materials are used when gas absorption leads to change in the, their Fermi level, change in the band gap, electronic conductivity, which is measured here in resistive sensors. In MXenes, actually, they're metals. Metals are usually not used as sensors. But you remember we talked about ability to tune the Fermi level by absorption, by surface chemical reactions here. And MXenes can intercalate or adsorb on the surface due to surface charge many molecules like acetone, ethanol, ammonia, and others, especially positively charged or polar molecules here. And their conductivity changes of the film where this happens. But because they're metallic, because they're highly conducting, there is a very low noise level. And you don't need to heat it up to 200 degrees C, for example, compared to many oxide sensors. So they appear to be attractive in this gas sensing application here. Again, based on their conductivity, change of conductivity that we know after adsorption intercalation, and their metallicity here. Along with the optical applications, biomedical application of MXenes are among the fastest growing at the moment and expanding here. Much of it started with using MXenes for photothermal therapy. And again, recall pictures that I showed to you of MXenes having plasmon resonance at different wavelengths, and a number of them have it in the near infrared or infrared range. For example, titanium-332 close to 800 nanometers, niobium-2C goes further into infrared. And they appear to be very efficient light to heat converting materials. And one of those applications is using them instead, again, plasmonic particles, metal particles, for destroying tumors when they ejected. Moreover, being two-dimensional, being able to efficiently adsorb molecules between the layers, it's possible to load them with drugs like doxorubicin and pretty much kill remaining cancer cells, which will not be destroyed by the using photothermal therapy effect here. So there are many papers and actually several review articles already on use of MXene for photothermal therapy, actually our other photothermal application, like for example, water desalination, but largely for those medical applications here. However, now let's look at the conductivity and biocompatibility. A natural application is implantable or epidermal electrodes. And again, this is an application where gold, platinum, silver electrodes are used to achieve good compatibility. What it appeared in the study done by collaboration with Flavia Vitale at University of Pennsylvania across the street, that MXene actually gives again better signal to noise ratio because of a better impedance matching between MXene electrodes and tissue in brain electrodes, but also in electrode for electromyography, electrocardiography, and other also epidermal skin electrodes here. And we're working with Susan Sandeman and her group at University of Brighton on using MXene in ophthalmology, when we can basically tune optical properties to correct vision defects in people in the lens here. And I can continue and continue, but what we are very much excited about at the moment in our group is developing a wearable kidney with MXene. And again, it may sound like a very anti-intuitive and unusual application for a two-dimensional materials, nanomaterials that you would not necessarily consider. But probably everyone knows that there are millions and millions of people suffering from kidney disease. You can see, at least in major American cities, dialysis labs everywhere, where people with chronic kidney disease have to go a couple of times a week and spend several hours in each session doing dialysis here. And actually, the problem has become more acute because of the current pandemic. About 30% of patients who ended up in intensive care unit with COVID have significant kidney damage and require dialysis. In New York City, hospitals were running out of dialysis machines during the peak of the pandemic in spring 2020 here. So what does prevent building wearable kidney? There is no good sorbent for urea. Activated porous carbon, which is excellent sorbent for majority of application, does not really adsorb efficiently very small urea molecules. MXenes appear to be a very good sorbent for urea. We published the first paper on the subject actually in 2018. Since that, we started collaboration with a major Korean company, and there is now a spin-off company in the US, Nephria Bio, which has been created to develop wearable kidney, actually much smaller than this one in Victor Gura's prototype I'm showing here to you, to improve quality of life and save life of people who suffer from chronic kidney disease here. So again, we hope materials that we develop will make an impact in that field here. There are many other applications I have not had time to talk about today. I would like to refer you to this very recent review in Science. It was published like less than 2 months ago, and it covers synthesis, properties, and application of this exciting large family of materials. We have written it with Armin Wahid Mahamadi, who is a research assistant professor in my group, and Johanna Rosen from Linköping University, Sweden. So again, I think it's a good source of up-to-date information, at least to start with, and find as a useful reference to read more. What is also important, slowly MXenes start moving towards practical application. There are more and more companies interested, and Terence Barkan the person who launched the Graphene Association, started Maxine Association to bring together industry, but not only industry, university, other users interested in developing application for Maxine. So it was launched in April this year, and hopefully there will be larger interest from industry. And of course, like any new materials, we're just in the beginning of the road, really. I mentioned from like 1,000 of possible stoichiometric compositions, just maybe like 30 have been produced. Couple of dozens of solid solution, mixed Maxines, and for several Maxines, up to 10 different surface terminations have been demonstrated. But it means that there are many Maxines to discover. I talked about hybrid materials and assembly in two-dimensional heterostructures between different Maxines, Maxine graphene, Maxine dichalcogenides, Maxine boronitrides. There are papers, there are publications in this direction, but there is still a lot to learn, both computationally, how to predict properties of those heterostructured materials, accounting for surface chemistry, accounting for possible intercallant, including water, that Jim Yuri discussed in his talk earlier in this session, and how to build them, how to benefit from properties those building blocks available to us today can bring here. It's also interesting to learn how to grow on a wafer scale carbides and nitrides. And it took quite a while to learn how to grow graphene, boronitride, dichalcogenide by CVD, single crystals, larger scale. It is still to be done for Maxines. Many of the properties predicted, like two-dimensional ferromagnetism, topological insulators, those are still to be experimentally demonstrated. Plenty of room for research for physicists here. Uniform termination of Maxines allow control properties better compared to mixed oxygen OH fluorine termination. Again, I did not talk much about surface chemistry today. There was not simple enough room, but it's really a way to control already available material through basically adding another level of control. Surfaces, chemistry, ligands, also including covalent attachment of molecules to the surfaces here. And of course, bare Maxine, I'm not sure whether they'll find many, if any application, but they're interested in for studying fundamentals physics here. But ultimately, those are materials that fit very well for flexible, wearable technologies. And this is where we expect the first applications, practical commercial applications are going to be here. There are many other problems to solve. And at the third international conference on Maxine last year, a group of leading researchers working in the field, including myself, we organized this conference with Professor Qin Huang from NIMTE in China. We actually made a list of more than 30 topics, and conference participants voted to basically arrange them in the order of importance. I know there is a lot of small text here, and don't try to read it. I would suggest you just go to our editorial in ACS Nano, which accompanied the virtual issue of ACS Nano on Maxines earlier this year. We have this list printed there, so you can access it, read it here, and if you're interested in tackling problems in the Maxine field, you already have a list of more than 30 problems that community is interested in, ranked based on perceived importance by the conference participants, and you will be able to start solving problems here, because of course, field of such a huge material field requires much more efforts. Compared to thousands of scientists working on single graphene made of one element carbon and maybe some dopants and additions here. And here you have materials made of all these transition metals with carbon, nitrogen, boron now is joining the game. All this possible surface termination, including OH groups and other things here. and all this variety of structures. Of course, this is a very exciting field for exploration, for discovery, for discovering new materials, new material structures, new composition, new properties, and of course, improving the current technology. Basically, I think we have building blocks for the future. And with this, I'm going to stop. Of course, all this work I was talking about today from my group was done by my PhD students postdoc. This picture was actually taken very recently, like less than a week ago. We had our first retreat after pandemic, when we were able, at least outside, to go maskless and take a picture where you can see faces of people and all together. We have also many collaborators, excellent, outstanding collaborators at Drexel and elsewhere. I'm a material scientist, material chemist. Most of the device and application work was done in collaboration with excellent colleagues at Drexel University, across the street, University of Pennsylvania, other US universities, national laboratories, companies, but also pretty much all around the world. Europe, Asia, Africa, you name it. Only in Antarctica, there are no research activities in the vaccine field so far, but this may become possible for some applications in the future here. And of course, big thanks to various US international funding agencies and industry for funding our research in that field here. And thank you very much for your attention. I'll be glad to answer questions.
Thank you very much, Yuri. Great talk, certainly a really exciting area. So I have quite a few questions here in the chat box. I'll ask them in the sequence I received them. So the first question is possibly asking you to maybe provide some more comments on the catalytic and photocatalytic properties of this mixing materials. It's from Sergey Nikitenko from CNRS.
Basically, if you look at materials that I showed to you, they are carbides and nitrides of transition metal. And many, especially say moly, tungsten carbides, have been known for a long time to be efficient catalyst, photocatalyst, and electrocatalyst here. I'm not an expert in catalysis. In my group, we work again in collaboration with Alex Voivodich, who does DFT prediction at Penn, and also colleagues at other universities in the US and abroad on, for example, hydrogen evolution reaction. What is interesting in MXene, for example, moly2C, the entire surface is catalytically active, unlike in dichalcogenides, where actually sulfur-terminating surface is passive and only edges provide catalytic properties. So this is one of the interesting applications. Second, actually, you can look at the MXene structures. It's a 1-1-1 slice of the sodium chloride cubic lattice. So you get a surface which is actually not usual in nanoparticles, nanocrystals that would grow in a different configuration. So you get entire surface. Moreover, you can have materials where, for example, you can embed in holes in the surface in vacancy of transition metal, platinum, or gold, making single atom catalyst here. And you can take solid solution and consider, for example, like a embedded atom, say, of tungsten in titanium carbide to be like a single atom catalyst here. So I think you get an idea. And of course, if this material is plasmonic, you can use it for photocatalysis using plasmonic properties, exciting materials. And surfaces capable of strongly adsorbed molecules and also possible electron transfer from the conducting substrate offer other opportunities here. So I think this is like a toolbox you have. Now, if you're an expert in catalysis or electrocatalysis, you need to think what reactions you can catalyze by doing this and how you can use those available tools. And what, for example, will be wavelengths needed for you to excite resonance, let's say maybe certain molecules, and select the right MXene. Or what kind of electrochemical reaction can be controlled and which, say, transition metal you need on the surface for it here.
Great.
Hope this
Thank-
provides some directions.
Sure. Okay, so let's move on to the next question. It's more specific to using MXene as a transparent conductor. I think the question says that the transparency of the MXene seems not as good as the ITO. Do you know what might be the limiting factor there?
Correct. And of course, you know, like, there are a couple of issues with transparency. And like actually in many properties of MXene, let me mention one very important thing here. We're talking at the moment about materials which are just in the beginning of their development path here. So we are pretty much majority of material experiment I showed to you, including, say, for example, this extraordinary electromagnetic shielding, were coming from like the first experiments made. There have not been billions of dollars invested in development of those materials. So there is plenty of room for optimization. And in many cases, honestly, we don't know theoretical limit to these things here. For example, like we have fairly broad resonance peaks. So we know that variety of surface functional groups, defects, for example, are responsible for this breadth. We get more ordered material. We have less light scattering or absorption. We will get, say, a more narrow plasmon resonance peak here. How we change the structure and composition, we can again tune these properties. And I think this is where this fundamental science is needed, that we can basically understand what is really the limit here. And we see some of this material being quite transparent, some of them absorbing strongly here. So I think this is this combination of both understanding what the theoretical limit is and improvement of structural perfection, surface chemistry control, that will eventually lead to, I think, drastic improvement in the behavior. And something else also didn't mention. For example, if you want to tune finely optical properties, for example, position of the plasmon resonance peak, you can also make a solid solution and you can shift those. So having so many degrees of freedom is a great opportunity, but is also a major challenge because you need to learn how to control all of them.
Thank you. So we have 5 minutes left. Let me ask the last two questions from the chat box. So the first one is more general, asking why is it rare for MXenes to show semiconducting properties?
Mm-hmm. Again, there are a couple of reasons for this, because computationally, majority of surface termination or mixed surface terminations that are produced at the moment here are expected to give materials with metallic properties. Second, also, we do actually have a large number of semiconductor and semi-metals. Take transition metal dichalcogenides, which have been developed, explored here. But there are no really two-dimensional metallic materials, moreover, easily processable from solution by method compatible with solution process and fabrication. So naturally, the interest was to exploring metallic conductivity, increasing metallicity and metallic conductivity of MXenes here. Definitely, it's on the fundamental level interesting to produce and study semiconducting MXene. Can they take applications away from, say, TMDs? I'm not sure. That's something, a question to ask expert in semiconducting devices.
Sure. That certainly makes sense. So the last question is related to the use of MXene for biological applications. So the question is whether the MXenes can be metabolized in vivo or in mammal body for drug delivery type of applications.
Yes, I mentioned briefly applications in cancer therapy. So there are quite a few papers on this theranostic application. That's, for example, photothermal therapy is combined with drug delivery. They can be metabolized in the body, but also interesting, some of them can be also easily tracked in the body. And that's kind of a combination. We still poorly understand the fate of each of those MAXine in the body, how it will basically depend on the type of material, particle size, and others. But one thing that also I didn't talk about today here, that in single particles, single air particles, MAXines slowly interact with water, oxygen. So, for example, if you take titanium 332 MAXine, we expect that over a period of time, they actually will be decomposing if they're single particles. It doesn't happen to thick films, for example, here. They will be decomposing, forming tiny titanium dioxide particles and carbon oxide or methane, which are basically biocompatible, and people studied titanium dioxide particles behavior in tissue in the body for a very long time. So again, we can build on this knowledge here, but definitely much more research is needed in that field, like in many other field of applications of MAXines.
Thanks a lot. I think we're doing perfect on time. And thank you, Yuri, again for a great talk, and also James, our first
Thank you for sharing the session.
Thank you. And thank you for sharing the exciting science and for the inspiration. And for the audience, I think you can come back for the other parallel sessions, and also we have a work session and keynote and plenary sessions tomorrow as well. Okay, thank you very much for your attention, and Jim and Yuri, great talks, and hope to see you sometime in person when the pandemic is
Thank
getting
you. Goodbye, everyone.
Bye.